So we're dealing with, I'll call it billion scale deduplication. It's a deduplication on one of our major data sets. And it's a billion scale, which poses real challenges. And that's what I'm going to talk about. I wish it was a trivial solution, but it's not. So who am I? My name is Idan. Nice family guy, 3 kids. Basically, or by education, I'm an economist. Turned data scientist around 5 years ago and love it very much. Kind of a geek, like a coding geek. Also volunteering in Eretz NGO for almost a decade, and #1 fan of #1 singer in Israel, Mini Beggar. So what is the motivation for our billion scale deduplication, or for the deduplication itself? So this is like a sample, of course, a mock-up sample of our data set. So what we see is that we've got multiple records per one entity. If you can see like Idan Richman and Idan Richman and like Smiley and such. And the information for a given entity is scattered around many records, okay? And they're not like real duplications, exact duplications. And we've got hundreds of millions of them, if not billion, plus. So this is the challenge. And entity resolution in general is like the technique to link those scattered records and to link and identify that these records are the same entity. Okay, although name can be a bit fuzzy or a bit changed. So this is the name of, let's say, the category for it. And the challenges that we've got are, first of all, fuzzy matching. So we can see the name can differ a bit, like at character level. You can see this one starts with an I, and this one starts with an E. And we've got non-Latin or accented letters. Could be different. We've got semantic matching. So let's say data scientist and data engineer. We could say these are the same semantically, or at least close semantically, although these are different strings. And we've got information extraction, for instance, from the email field. We can see, like in this, we have a smiley, but I can extract the name from the email, or the company from the email domain. And doing that for billions of records or hundreds of millions, and that is an issue. So we need to do it efficiently. We can't just go and do it one by one, compare every record to all other records, right? So this is a simple case. Let's say I'm taking the first record, the one in gray above, and start to compare it with all the others, computing some distance scores. Let's say, I don't know, Levenshtein distance or whatever distance you can use. But this doesn't scale, right? Because if I'm doing every record against all other records, this is like a major complexity. And for 100 million records, for instance, and we've got more of them, so it's like 5 quadrillion, which is 15 zeros after comparisons. This doesn't scale. You can't do it. So one of the, let's say, fundamental or the common methods to handle such, let's say, complexity is to do blocking, right? Or let's say clustering, or reducing the search space. So I'm not going to compare one to all the other. I'm going to compare it for a small subset that I identified that they can be similar, right? So for instance, let's say I'm using the initials. Let's take the first letter of the first name and the first letter of the last name, and I'm grouping them by those. So I've got like IR, and I'm comparing them both, okay? So each record, I compare only to the other records in the same block or cluster, whatever. And we can see this is suboptimal, right? And even if you've got large data, so the blocks will be even large, right? And if I'm splitting it for many blocks, so it won't be efficient. So we need something better, right? Something more advanced. So here I, let's say, enter ANN, which is not artificial neural network. It's approximate nearest neighbors. And it's approximate because, let's say, unlike KNN or so, we're not doing an exhaustive search, again, comparing and searching for the whole distance between each record to all other. So we're doing something approximate. So we sacrifice some accuracy, but we gain a lot of, let's say, performance and speed. So we can actually scale it up. Before moving forward with ANN, just a quick interlude on embeddings, right? Or let's say representation learning. So for instance, here I'm taking a job title, which is part of our data, right? Job title of a contact. And what we can see here, for instance, it's a clustering. We did embeddings for job titles. So similar titles will be closer in space. And this is like a 2D projection of the entire space. Let's say I've got 100 dimensions. So this is just 2D. And we can see similar titles are similar, closer to each other. So we've got like human resources and those yellow. So we've got the teller, underwriter, bookkeeping, like more finance or banking stuff. And let's say teller will be close more to bookkeeping and not, let's say, storyteller, which is text-wise can be closer, but storyteller and bank teller, completely different things, right? So storyteller will be, let's say, off the grid here, not near. And what we will do in ANN, so we're searching in that space for each vector for the nearest neighbors of it. So the search results that we will get is as good as our embeddings. So if you've got like poor embeddings or poor representations, our search results will be poor as well. In terms of similarity measures, most of it we use the command. So we got Euclidean distance or cosine distance. So cosine distance is just computing the angle between the vectors and doesn't take care of the magnitude of the vector. So it will come handy later. And for instance, if you look at those Elon Musk old tweets, so one says like one word dog and no highs, no lows, only dog. So if you compute the Jacquard distance, which is the set similarity, so we've got only one common word, right, dog. And the Jacquard distance is quite low, right? Because only one word among like 7 unique words. But let's think a bit like fundamentally or semantically, those tweets are quite similar, right? They talk about dog. This is what's important. So this is the importance of the semantic or the representation of what we're looking for. So the main algorithms we use for ANN, and those are the most common that you can use, and all the state-of-the-art algorithms are based on those, mainly on like IVF and the HNSW. So we've got LSH, which is, I think, the oldest one, and it has a lot of literature on it and a lot of enhancements and developments on it. It's a bit suboptimal comparing to the others and less used, but the idea of LSH is that it is locality sensitive hashing. What it means, so usually when we are using hash functions, right, when we want to minimize collisions, right, we want to hash stuff that they will be separate, and in locality sensitive hashing, we want to hash stuff and closer let's say entities should be hashed together, right, and not separately. So we want to increase collisions for closer stuff, for closer entities. The other one is inverted file index, and HNSW will go for them further. So for LSH, for instance, we can see here, I'm not going to dive into it. It's not the main topic of it, so I just want to go briefly on it so you can get the concepts. But there are a lot of good resources. Also, I've got a slide at the end. For instance, this one or this illustration I took from Pinecone. They've got like a whole learning center on the website. They're like a commercial company that does vector database, and they've got good resources, very good resources. So if you've got signature A, let's say, so this is Elon Musk's first tweet, and you divide it to subvectors, you hash them, and you hash them into separate buckets. Now we've got signature B, and you can see here that in some of the buckets, in some of the let's say, hash functions, it's go for different buckets, but on the red one, it goes for the same bucket, and that's how we know that we flag those two signatures or those two texts or vectors, whatever, as comparison candidates. Okay, and this is what we want to do. So we want to take two records that we've got. Let's go back for our initial database, okay, of contacts, of records. Remember Idan Richman, Idan Richman, whatever. So we want to flag two records as candidates. And later on, we will go over those candidates and perform a more deeper comparison to see if they are indeed the same entity. Okay, we don't want to do this deeper comparison for all records. We can't. So this is the, let's say, the purpose of ANN, right? To reduce the search space that we're performing. HNSW is a graph-based algorithm. And what it does, so it constructs a graph when you train it or build it. And then whenever you've got a query vector and you want to find its nearest neighbors, so you traverse the graph and you can find the nearest neighbor. The problem is that when you've got like long path, so it takes a lot of time. That's why some smart guy find out about hierarchical navigable small world graphs. And what it does, so it allows for each layer to go, let's say, the top layer is doing like big leaps across the space. So you can, every time you go down a layer, you go into finer detail or finer distances. And that way you can like skip very fast from here to here and find the nearest neighbors. The next one is inverted file index. In this case, we take the space, we divide it to cells. It's based on Voronoi cells or Voronoi diagrams. And the property of those cells, let's go for here. So each point in space, for instance, if it lies inside those red cells, so it means that it is the most closer to the centroid of the cell, all right? Like, let's think of it like k-means, right? So each point in the red cell is the one that most close to this centroid and not the other centroids. So what we're doing, we're dividing the space to those cells. And now when I want to find out, for instance, here, I've got this query vector. And who are the nearest neighbors for that vector? I don't need to search for the whole space, for the all records in all space. I'm just looking at the records inside the same cell, right? But what happens if I'm looking for that query and I've got a nice candidate here, right? So it is closer, for instance, here instead of the one from inside itself. So you can define, there's like a nprobe parameter that you define how many adjacent cells you need to look for. So you can look not just inside its own cell, but also in the cells near. And of course, if you will choose like large nprobe, it will take more time. And if you choose like nprobe infinity, it is the same as doing like exhaustive KNN, right? In terms of comparison between the algorithms, so there are trade-offs, right? So for instance, HNSW takes a lot of memory, which is a problem when we're dealing with large data sets. But it is quite fast. Also IVF, it is quite fast. This is like milliseconds per query. And of course, what you say, your mileage may vary between data sets and stuff. If you compare it for an exhaustive search, and this is only for a 1 million data set, 1 million points, so we see a huge improvement in search time. And this is very, very crucial if you want to do it for hundreds of millions of records, right? So this is very critical. Just back here, so what we want to balance the speed and the memory and we want a good recall, right? The recall, if you go exhaustive, so it will be 1, because this is, we search for everything. If you go approximate, so we sacrifice some recall, but we gain speed. Now we're getting for the dedup pipeline that we're doing, right? So these are, let's say, the 4 main steps. So the first step that everyone is aware of is like a lot of cleanup, a lot of preparation, doing text embeddings and embedding the name, the company name, the job title, and whatever data that we've got for each record. The second step, and I think this is the most crucial one, or the most stuff that is not usual, is the ANN one, right? So we need to find good match candidates. And after we find those candidates, we can go and pass it for a classifier. So the classifier, as I said, is something that takes and performs a deeper comparison of the records. So if I'm doing the ANN or the approximate on the embedded vectors, I might lose some, like the embedded vectors are not, let's say, not perfect for comparison. So when I go deeper, I can compare like 2 strings with different distance measures. I can do a lot of, let's say, more computational, costly operations, but I can do it for a lot of comparisons, right? Because it takes time. So I need to minimize the search space that I'm passing for the classifier, and like feature engineering, etc. And the last one, after I'm finding matches, so the classifier, let's say the classifier gets 300 candidates. And then it says like, okay, only 2 are a good match. So some might be similar. So for instance, I get Idan and I don't know, Ido, right? Good, thanks. So I get Idan and Ido, and the classifier, the ANN say, those are similar, right? ID, N, O, whatever. But the classifier will say, this is not the same person, right? I know that Idan is different than Ido. It's not the same person. So the classifier should give me a better result. And then it is passed for the merge, and the merge goes and take all those different entities, like the table I showed you at the beginning, and merge them all to one canonical contact. So now instead of having 5 records for Idan, I'm getting only 1 record, because this is 1 entity, not 5. So the ANN, and as I think this is the most critical part of it, we need to choose the stack, what we're going to use. So there are different tools, there are different packages, and we need to choose. So we experimented with some of them. We looked at like record linkage and Splink and data sketch. This is LSH. Those are all like Python packages. Some of them are not really ANN, as I showed you before. Some of them are just doing simple blocking, like I showed you with the initials. I think the one that uses ANN with like state-of-the-art are a Spotify Annoy package, and HNSW lead, and FICE, which is like a Facebook AI similar to search. And our requirements was that we don't want to rely on in-memory, because we're dealing with a large data set that doesn't fit in RAM, right? So I need a package that doesn't rely that I have everything on my pandas data frame and I can pass it to it. I need something that knows how to handle batches or whatever, and that doesn't fit in RAM. Also, I need something that supports updates. Right? So let's say I'm doing the deduplication today. Tomorrow I'm getting new data, and I want to update or check this new data on my current indexes and not do the whole process all over again from the beginning. So I need to support updates or deletions. And it needs to be fast, of course. That's, for instance, why data sketch LSH is not suitable, just too slow when the data passes like 1-2 million records. So after a bit of experimentation, we decided to go with FICE and the IVF algorithm. That's the tools that are the least, or let's say the minimum overhead. I think also Annoy is a good tool. And the HNSW also, it's a good algorithm and a good tool, but it requires more tweaking and more playing around if you want to use it with, let's say, out-of-memory setting. And FICE also have a GPU implementation, which can give you a big speed up. For my initial plays or playground, you get like a 3 times speed up, which is also very crucial. And just to know about the space, so you can see that lately in the past, I don't know, year or so, or even less, like 6 months. So a lot of like Elasticsearch and OpenSearch is starting to put ANN capabilities into their systems, into the search engine. And there's a growing field of, let's say, vector databases that allow you to upload vectors, do simulator search, and all kinds of those stuff. And it should work like out of the box. We didn't try those commercial solutions, but you can see them here. And they might be good, I don't know. So the first phase of doing the IVF, so we need to train or we need to fit the space, right? So we need to find those centroids of the cells. So later on, we can pass those records, like the vectors of the records, and it will assign them to those different cells, right? We said we need to reduce the search space, so we need to train it. But for fitting it, I can't use the entire data set, right? So I need to find like a sample, a good sample to train it on. And a good sample is not just take the first 1 million, right? Because the first 1 million can be only names that start with A, right? So I need to find something representative, the same distribution as my whole data. So it needs to be limited by size so it can fit into RAM. So I just took the first, like as before, the first letter of first name, first letter of last name, and also for the company name or job title. So I get like a couple of dozens of, let's say, those bins. And I limited the size of the data. So it can be like just 1 gigabyte, and this can be tweaked. And this is how I trained or fitted the space. And again, what I wanted to accomplish is to have a representation for the whole space. That's what I cared about. And the second step is to try and start indexing those vectors, right? So this is the core element, the index. And then when I'm having like a new record, like I'm getting a new record and I'm feeding it into the algorithm, it can tell me who is that record nearest neighbors. So we need to index all the neighbors, all the records. And I think who among you that use like Elasticsearch or so it works similarly the same. It does indexing, it indexes the data, and then it looks for the nearest neighbors. And again, the data is too big for RAM, so what I did, I took the Parquet file, right, the folder that Spark saves, and just went file by file. And you can see the file size is manageable, of course, for RAM and Pandas. So and start to add it to the index. And this is the way that you can do it for the entire, a lot of gigabytes of data, and not just in one go. Also, we need to consider for the index size, because even I can add it in batches, but at the end, I've got like an index file or an index that we need to search. And all those packages, or at least what exists today, just use it like in memory. So I need the index itself to stay in memory. It doesn't know how to read it like on disk or so. There are some implementations, but again, not open source. So what I used is something that is called product quantization. And what it basically does, so it takes, it's like a compression algorithm. It takes the vectors and it's kind of compressed them. I'm not going to go into the details in exact, but it's like divides the vector into parts. And then for each part, it does some clustering. Okay, so for the first part, it trains like a clustering algorithm, and then it stores a cluster, an ID of the cluster. So it compresses the data a lot, and you can reduce the index size like in large magnitudes. For instance, like a 30 gigabyte index file turned to 3 gigabyte, which is again more manageable to use in memory, right? So, and as the data grows, this is something crucial. Again, comes at the expense of accuracy, right? So, no free lunch. Another thing that we encountered is the necessity to use, let's say, fusioned or concatenated vectors. We can embed names separately. So the embeddings, as I showed, or like job titles, as I showed you before. But if I'm going to look now, I've got, like, let's say, Kobe Coin, right? It's a quite common name. And I'm going to look, okay, who are the neighbors of Kobe Coin? Give me all the original records of Kobe Coin. I will get like many. Some of them are not relevant because I'm not looking for Kobe Coin in general, right? I'm looking for a Kobe Coin in a certain company or a certain job title, right? Because those are the similar records of it. So this is what I care about. So what we did, we took the vectors of the name, let's say 100 dimensions or 160 in that case, and I concatenated them one time with the company vector and one time with the job title vector. So I ended up with two distinct vectors of 260 dimensionality, and those are my indexes. So when I'm, let's say, looking for the nearest neighbors, I do it on two indexes, name plus company and name plus job title. Yeah. Okay, so if you can see the chart here, so we see the search speed, right? So we see as the number of vectors grow in my data, and this is the millisecond it takes to do the query. So if I'm using the product quantization, let's say in comparison for a flat exhaustive search, there's a huge speed up gain. And I think the last thing before I go into some questions, so it's about full record fetch, right? Because the index, product quantization, everything gets compressed, everything goes in memory, this is fine. But now I've got like a billion records data set, and I just want to take 300 candidates for that query, right? So get me 300 records from a billion records data set. It can take some time, and if I do it not just for one query, right? I want to do it like for a lot of queries because I want to go and traverse all my data set quite quickly. And this is not just do read Parquet or read CSV or whatever for I don't know, dozens of gigabytes. It takes time, right? So we need some fast solution. So we experimented with some solutions, and the one that we find like works best is using Redis, which is like a key value in memory database, and it's like blazing fast, and it is awesome. I think we can skip that just to leave some time for questions. About the classifier, so this is the feature engineering. As I said, we go deeper into comparison of the name, company, title. So I've got like a lot of string matching or string distance measures. And this is, again, we need to do some feature selection, and we did, because it takes a lot of time, and some of them are redundant or correlated, and we need to count every millisecond. So we chose only the important ones. And we also ditched the cosine similarity because it means also we need to store our original vectors in Redis, which is very expensive. So we ditched that. I used XGBoost model, and just for instance to show you how a good match or what the classifier can match. So we see we've got a lot of, let's say, string differences between those two records, and even the phones are different. So just a simple, naive solution would never find this match, right? But using all the stuff that I described, so we were able to match it. Okay, this is best show ever. And just a quick recap. So about the billion scale, going billion scale, what matters is that we need not to rely on in-memory solutions, right? We need to go by batches. We need to go product categorization. We need to use fast retrieval. So it's not just like pandas, iLock, because it doesn't work when you use it, when you're dealing with those massive data sets. And I think that's it. Those are resources and questions. I'll keep that if you want to. Also. Yeah.
Try different. I have two questions.
Yeah.
One is, did you try different similarity metrics first?
Can you elaborate?
Distance and something else. You saw some functions. When you actually extract the features, did you try to extract them using different methods?
So doing like Levenstein distance on the text themselves?
For example, and then doing something else, like having a membership.
Yeah, I'm doing it in the classifier part because I can't do it. You can't do Levenstein distance for each record on all other hundreds of millions. Yeah. So that's what I showed. Like in the feature engineering, I did like multiple features and then feature selection to see which are the valuable.
So that's the first question. Second question is, why do you call it the approximate nearest neighbor? Because today you have KD trees or ball trees or whatever. They are implemented in Python that you can actually use and find the exact neighbor. Why do you call it approximate? What's the approximate?
It's approximate because it does some approximations. You can't reverse, you can go with KD tree. It's not scalable in terms of let's say milliseconds per query. It will take too much time with those massive data sets. At least that I'm aware of. You can't go exhaustive search.
So we should talk afterwards as far as I know.
KD tree, I don't think it's not approximate. I doubt it. I will try, but I really, really doubt it.
Okay. Yeah. First of all, great talk. First, two questions. It looks like a very complex pipeline, and the actual noise generation of this data is sometimes users are making mistakes in entering it. So I'm curious, first of all, what was your benchmark, your first and foremost method to compare to this complex pipeline? And the second one, why didn't you use, or if I understand it right, entity level information like comparing companies, comparing job titles, and comparing maybe names and addresses on a different layer or dimension in order to relax this problem?
Okay, so as I said before, comparing companies, some companies are small, like 10 employees, so that might be fine. But let's say in my previous company, Dell, it's like you've got hundreds of thousands, not hundreds, tens of thousands of workers. So I'm not sure it is feasible. And also in that manner, you see a lot of manifestations of the company name. So it's not just Dell Technologies, Dell Inc. You've got a lot of those fuzzy, let's say, differences. So it's harder, but it might be a good idea. I'll think about it. And for your first question, remind me.
What was your benchmark?
Oh, the benchmark. Yeah, so basically it's not a label data set, right? So my only label or things that I can use to link to records are, let's say, phone number or email. And that's how I train my classifier. So I take record that has the same phone number and similar, I use some kind of a fuzzy matching score, similar score, because there are some phones landlines that are shared among like 100 different names, different people. So I can't tell the classifier those are the same people, right? I'm just linking it for mistake. So that's how I quasi-labeled my data set. And that's how I built also my test set and all. But at the end, you need to manually inspect it. And also in terms of that, so we want to favor precision over recall, right? Because I don't want to merge two distinct entities. I want to be safe, and even if I'm keeping the same entity on two records, it is better for me, I think, business-wise, than to merge entities that are not the same. Yeah, I don't know how much time we've got left for more questions, so stop me when you want.
One last question.
One last question, yeah.
Small two question. You mentioned that you need a good embedding vector. How
Yeah.
do you measure the good of your embedding? How do you know that?
Oh, yeah. How do you measure the goodness of embedding? That's a very good question, I think. In general, how do you test embeddings? Yeah. My answer right now is that I just look at the results and it looks good. I haven't done some let's say methodical test or so to check it. It just works okay.
How did you combine those two vectors that you mentioned from?
Naively concatenated them, like first, second, just concatenated, and then used cosine similarity, because if you use Euclidean distance, so sometimes like the first part of the embedding is taking over because it's a different embedding space. So you need to use cosine and not Euclidean. This is important. Thank you very much. You can approach later for more questions. Thank you very much.